In this video, I'm going to introduce the topic of exposure and dose from brachytherapy sources. In the previous videos, you've looked at some common sources that are used, and you've learned the mathematical descriptions of decay, and you know this formula for activity over time. You'll see the exponential decay here. And so our goal here is to take what you know about activity and to turn that into a dose in a patient. We can do that, but we have to go through an intermediate step with this, which is the exposure. I'll explain about what that is, and that's actually exposure in air. And with these concepts, we'll be able to figure out going from activity to dose. So let me write this schema up here at the top of the screen. And we're going to start by considering this quantity here in the middle, the exposure in air. And I'm going to explain this by walking through a little experiment. So imagine we have a little chamber full of air here with an electrode in the middle with a voltage. And there's air inside the chamber, an air cavity, and I send photons in like this. And you'll learn later that they interact in the air and create electrons in the air, and those electrons move toward the anode because of the voltage. There are a lot of electrons in here. Collectively, this is the charge, right, with this symbol. It's a Q. So with that, you can see what exposure is. Exposure, which has the symbol X, is charge per unit mass of air in the chamber. So if you know the mass of the air, you could calculate the exposure. What are the units? A good one is the Rankine, which is commonly used. It's 2.58 times 10 to the minus 4 coulombs per kilogram by definition. Seems like a little odd number, but it came from an old definition, which was 1 Rankine equals 1 ESU per centimeter cube in air. That's the old CGS units. Those are old, so we're going to go with the newer SI units. So that is exposure. And now that we understand exposure, we can start to work towards dose. So one thing here is we don't usually talk about exposure. We talk about exposure rate usually. The exposure per unit time. And that's written like this, X dot. The dot there means per unit time. So it's equivalent to the change in exposure per unit time. You can write that for any variable. So the exposure rate can be written as a formula, which looks like this. So it's proportional, and the proportionality constant is this gamma. So it's proportional to the activity of the source, sort of makes sense, right? Divided by the distance squared, the distance you're away squared. This proportionality constant, gamma, is called the exposure rate constant. It's a property of the source. Each source has a different exposure rate constant because for a given activity of the source, you can have a different exposure depending on the energy of the photons or other particles that are coming out of the source. So let's take an example. So radium has an exposure rate constant of 8.25. And the units here are Rankine centimeters squared per hour per millicurie of, or if you're talking about radium, you sometimes say Rankine centimeters squared per hour per milligram of radium. And for any given source, then, we can talk about the milligram radium equivalent of that source, often written like this. That's simple. It's just the exposure rate constant for the source divided by the exposure rate constant for radium. So how much more, say, powerful is that source than radium times the activity of the source. So if you have a higher activity source, of course, it has a higher milligram radium equivalent. So I'd like to spend a minute talking about this 1 over r squared factor. That is the inverse square law. And we need to understand it, so I'll review it for a minute. So basically the concept here is that anytime you have some source emitting photons, they're being emitted in isotropically in all directions, you can essentially draw a shell around that source. So let's draw some shell at some radius r. Now let's figure out what is the intensity of photons at that shell. So first of all, it's going to be the initial intensity from the green source per unit area of that shell. Okay, that's like the number of photons per unit area. So what's the area of a shell? Well, you'll remember that for a shell of radius r, the area is 4 pi r squared. So the intensity at any radius r is some constant number divided by r squared. And so that's the concept, is that the intensity falls off like 1 over r squared. So we've got here an expression for exposure, but that's not very useful because we don't deal with exposure in air. What we really want is dose in water or dose in tissue. And so we need a formalism to connect these two together. And I'll walk through that formalism. That's from this report, which is AAPM task group number 43, TG43. And if you don't know about the AAPM task group reports, you should. There are many of them, hundreds actually, but they're often very readable, and they're really a definitive guide to clinical aspects of medical physics. I'll walk through in a very simple way the TG43 formalism for dose calculation. And what that's going to do is connect exposure to dose. And we start out with the fact that the kerma, the kinetic energy released per unit mass, is equal to the exposure times the amount of energy it takes to ionize an electron. W function, W over E. This is actually the collision kerma in this expression, and we'll talk about that in much more detail when we talk about radiative loss in tissue, but for now it's just the kerma. And then you can of course relate the rate of kerma to the exposure rate. Those are both rates. Okay, now in the TG43 formalism, we actually work with a related quantity called the air kerma strength. That's given a special symbol S, SK, for the kerma. And this air kerma strength is equal to the kerma rate at some distance L. And you do L squared because of the inverse square effect. So you can write this out then using the equation above. So exposure rate times this WE factor times the distance L squared. And then and these are just numbers. And you can calculate this out, the W number and the L, which is defined in a meter. And when you multiply those numbers out, you end up getting the exposure rate in air times this number, 0.876. So the exposure rate is in Rankins per hour, and this factor is the conversion of centigrade per Rankine at 1 meter in air. We're going to calculate the dose through the AAPM TG43 protocol. This is the revised version, published in 2004. So TG43 says that the dose rate from a brachy source, you start by starting with the air kerma strength in units of U, and multiply by the dose rate constant. Okay? Now that's specific for each brachytherapy source, and it has to be measured or provided by somebody. And then you multiply by the big G. Okay? So that's the geometry factor. It's going to tell you about the geometry from the source, times little g. That's the radial dose function. It tells you how fast radiation dose falls off as a distance from the source. And finally, multiplying by factor f, called the anisotropy factor, meaning that dose from sources is not isotropic. It's not the same in every direction. It varies as a function of distance, position. Now finally, total dose, that's often what you want to find from an implant, is the total dose from a permanent implant, for example. And what we gave you up above was dose rate. So from dose rate, you can get the total dose. It's just the initial dose rate, d0 dot, divided by lambda. That's it. Or you can rewrite this, since you know what lambda is. You can write it as 1.44 times the half-life. I'd just like to stress here that this is for permanent implants. That is where you put the seed in and leave it in permanently. This would be the total dose over the lifetime of the implant. Also, you can find the dose at any time t, after some time t from an implant. The dose at that time is equal to the initial dose rate, d0 dot, divided by lambda times this formula for exponential fall off. So now I'm going to talk about each of these factors one by one. We've already talked about the air Kerma strength. I'm not going to spend much time on this capital lambda, the dose rate constant, because in essence it's very simple. It's just a number that's measured and or calculated with Monte Carlo simulations for each source, and it's given to the user. But let's go on and talk about this capital G, the geometry factor. So G can be written like this. G is actually a function of R and theta. I'm going to define what those are right now. So let me draw a source here. This is a brachytherapy seed. And you're going to go from the middle and go out some distance in that direction and in the other direction. And here you want to calculate the dose at this point, and that's a distance r from the center and an angle theta. So that's what r and theta are for calculating dose at this particular point in space. So first of all, this G factor ignores scatter and absorption. That's important to remember. Scatter and absorption are taken into account by the other factors in the big long equation I showed. So G can have two approximations. First, you can approximate it as a point source, if it's brachytherapy source. And that's very simple. G is just 1 over r squared, right? It falls off like r squared. The second approximation is that G could be approximated as a line source. In that case, the formula is some factor beta, that I'll show in a minute, divided by L, the length of the source, divided by r, times sine theta. And this beta factor looks like this. If this is the source and you're out here at some point, beta is the angle that's subtended by that source at that point distance. So there are two different ways of treating G. Now, more properly, G is usually written like this: G divided by G of R0 theta 0. G of R0 theta 0 is some reference point where you refer to. So where is this reference point? You come out transversely to some point R0. That's the reference point that is 1 centimeter away from the center. Now we're going to go on and talk about this factor small g, the radial dose function. It accounts for absorption and also scatter in the medium where the brachytherapy source is embedded. And that's going to depend on the properties of the radioisotope, in particular the energy, as we'll see in a minute. If you have a source here, the G is just a function, as you go out from the center, just a function of the radius along that line, the distance r. Okay, so here's a plot of these different G factors for 3 different isotopes. So look at uridium here. It has a fall off that's not very steep with radius. right? That's because iridium is a high energy source. It's not absorbed or scattered much in the medium. Compare that to iodine. I-125 falls off much more quickly, and palladium much more quickly than that because the energies are lower. All right, now let's go on and consider the last factor, F, the anisotropy factor, which again is a function of the distance r and the angle theta in the geometry that I drew before. So the F factor is strongly affected by self-filtration and absorption, or attenuation rather. And so let me try to draw what that means in a picture. Here's a seed, one of the old iodine seeds. As you go out some distance along here, you'll see it penetrates through the shell of the source, right? As you go at different angles, it's penetrating through different distances through the source itself and the shell. And so you get more attenuation as you go out along towards the tip of the source. And that's so self-filtered. And you could draw another picture of that. Let me draw the seed down here. And let me try to draw an isodose line around that. So let's draw the two axes here. And then if I start at the end of the seed over here, I'm going to have kind of like a low dose, and it's going to bulge out and tuck back in on the ends. So it's like a lower dose near the ends. That's the anisotropy. So it's a strong function of the angle. Also a function of the radius, though, because as I go out farther, if I drew an isodose line out here, it'll look more like that. If I go far enough away, it looks like a point source, and it's just a circle, right? Okay, now there's another problem here, which is that sources in an actual implant, they come in at all kind of different random angles, let's say. And it's often very hard to tell what angle the source is at from radiographic imaging and so on. So if I'm looking out here at some point, I would be observing these sources each at different angle to the source. So the anisotropy factor would be different for each of these four sources here. So how do you solve that? Well, the way is that you average over all angles. And so then this anisotropy factor, the F, is then replaced in this case. It's replaced by an anisotropy number, we call it phi, and it's just averaged over all angles, but it's some function of the radius. So there you go. Some of the basic concepts in brachytherapy dose calculations. Like I said before, we're going to get into this in more detail in later series, but I do think it's nice to have paused and given you at least some flavor of the fact that what you're learning with these fundamental physics comes very quickly into a practical clinical translation for patient treatments. So with that, we'll stop with this concept. I'll leave you with some further reading, and we're going to go back now into some of the more basic stuff in the next videos. Thank you.